Hello, everyone. Um, I'm Shishin, and I would like to present section number two. This section is called tangent vector. I will quickly go over some basic concepts you might understand those easily. First, definition about the tangent vector. For a tangent vector, which has two components. The first is the vector part. And the second is the part, is the point where the vector applied to. The point is called the point of application. This means for each point given in three-dimensional space, we can have a point called P, and this point we can apply a vector, which is V. So that will be vector VP. So next, if we have some tangent vector, then uh, a set of this kind of point will uh, will form a tangent space. A tangent space is all kind of tangent vector. Uh, So if we can write it like a T with P and on R3 dimension, three-dimensional Euclidean space. So all this kind of vector applied to a point P will form uh, tangent space. This is easily to understand with a graph like this. If we have a point P, and we can have sorry, different vector applied to this applied to P. So we will have a, a vector space. So so the point P, you can easily to understand by if the point P is in the origin, it's just uh, the regular three-dimensional Euclidean space. So there's every time we define a space, we usually want to define some operations come with the space, and the space which is called tangent space FP, which means we can have infinite many of this tangent space. So if this kind of tangent space on a specific point from vector space. And for vector space, we can have two operations, which is addition and scalar multiplication. Okay, so you can actually you should rigorously you should verify those are well defined, and they actually are vector space. Vector space satisfy. I think I remember there's 8 axiom, so we should check each one, and we will prove it's a vector space. And the next thing is vector fields. Vector fields have the fields of name of fields. However, this is just a function. This is important. We say it's the function. This is the function. Actually, uh, uh, actually, for each of the function is a relation between two sets. If we have some basic knowledge about set theory, the function is a relation of two sets. So one is the domain, one is the range. Okay, and the function have for each element in the domain, we have a uniquely corresponding element in the range. So if we want to define a function, we will first understand what is a domain and what is a range. So the domain is easily to know because we want to have a vector. We want to have a vector field applied on any point in three-dimensional Euclidean space, and the output should be uh, a tangent vector. Output should be a tangent vector. So what is a tangent vector? Based on my understanding, a tangent vector, if we want to write a tangent vector, it should be like a, for example, 1, 0, 0, and p. So what is this? This is a vector come with a specific point. So if we can easily to understand, we can write it in this way, and P1, P2, P3. So this will be a Cartesian product. So based on my understanding, this is not on textbook. So any point will correspond to a three-dimensional space, but they are in a Cartesian product, and the operation is just like we define operation in a function. So if we have a function with x plus f plus g, so applied on x, and we will have f of x plus g of x. So this is easy to understand. And we have a scalar multiplication. Why is it called scalar multiplication? Because f is a real valued function, which means we will you give some point, it will give you a real number. So this is how we define the vector fields. And then we have another definition, which is called the natural frame field. Natural frame field is just we can have, for each point we can have a standard. We can have a standard orthonormal vectors applied on each point. So you have zero origin, and with a natural frame field, you will have the standard x y z coordinate system, and but if actually you can set your origin in any point in three-dimensional space. So this is gives our idea about a general coordinate system. And the last is the lemma, Euclidean coordinate function. This is important. It is use both what we have defined from vector field and a natural frame field. So for a given, if we given a vector field, we know it's a function, and we can find we can say it is uniquely determined by three real valued function, and we can know it can be decomposed in this way. So this is we can give another name called a decomposition of a vector field. This is easy, is also okay. Decomposition of a vector field, general or arbitrary vector field into natural frame field. So for each u2, u1, u2, u3, they are natural frame fields, and it can be get a linear combination of those. So there are the important thing. It is uniquely determined. So now let's understand this formula. So V equals V1 times U1 plus V2 times U2 plus V3 times U3. What is this means? This means two functions are equal. So what? Because the right side is a field, the vector field. The right side is also a vector field. Why? Because U1, U2, U3 is just the natural frame fields. Natural frame fields is a special case of vector fields, right? And then what is this? V is a real value function, and V times U1 is what we have already defined. It's just the operation of a scalar multiplication of a vector field. So this is will be still a vector field. And then what is these two adding up together? This is the two vector field added up together. A two vector field added up together is still a vector field because we know vector fields forms uh, follows a function. This function will still the same will still apply on the same domain and the range. So this is this. So if we want to show these two function are equal, we want to show they have the same domain, and for they have the same domain apply on same domain, and for each element in the domain, their output will be the same. So we want to show this it should be proof should be uh, something like we want to prove two functions are equal. So I don't like the textbook proof. I rewrite my own proof on this. We want to prove something is uniquely exist. So there are three uniquely determined. So this is a uniquely existence. So first, I want to show it is existence. If we want to show something is exist, so we want to find something. This is easily to know. If we want to let UV3 we want to set UV V1 V2 V3 satisfy this equation, then from the right side will equals is a function. So for given this is I didn't write it very rigorously. Actually, we should claim P is an arbitrary element from R3 because we all know this is upon R3. This is upon R3. So we can find the element arbitrary element P, and for arbitrary element P, we have this function apply on this. We want to show the output is exactly as the output of V of the vector field V. So we'll give it input. So we want to analyze the output. Based on what we have, what we defined about the addition of two vector field, it should be like this, right? And then based on what we have already defined, we can say you can connect this uh, with this, right? This with this. And the next is multiplication of multiplication of the scalar multiplication of definition of scalar multiplication of a vector field. So this is just another operation definition. And if we because we know U1, U2, U3 is, so we will plug in U1, U2, U3. Finally, we will see it's just exactly like the output of VP. So this proves if we let V1, V2, V3 satisfy this condition, then we will have this equivalence holds. However, we didn't say the uniqueness. So next we should prove the uniqueness. Actually, the uniqueness holds because of the definition of function. The function, what is the definition of function? Function means if we give it a point in a domain, we can only have uniquely corresponding element in another set. So suppose we have a different V1, V2, V3. We call it V1 prime, V2 prime, V3 prime. Also satisfy this condition. Then we from also we from the right side. The right side can be read like this. It's just follow the exactly thing we did before. So we will finally uh this form. After we have this form, we because we know these are equal. Yeah, this is because because our the hypothesis. So we know this is equal. And then what is V of P? V of P is uniquely this. Because we know we already have V1, V2, V3, and suppose we have another V1, V1 prime, V2 prime, V3 prime. So this is meaningful because this is from what we have already proved the existence. So this is already exist V1, V2, V3, and this is the only one where VP can be equal to because the function. So based on uh, based on the equivalence of two Cartesian product, this the each corresponding the same element. So V1P will be equal to V1 prime of P will be V1 prime V1 of P. So this is next will be similar reasoning. So this is my presentation of 1.2.